Okay, I hope my slides are visible and I'm audible to you.
Yes, madam. Good evening, madam.
Okay, so welcome to the 11th tutorial of this course, Reagents in Organic Synthesis, which is conducted by NPTEL, whose course instructor is Professor Subhas Chandra Pan from IIT Guwahati. I'm Deepika, your PMRF teaching assistant, and I'm doing my PhD in chemistry at IIT Bombay. So, for the past few video lectures, we have been discussing about various organometallic reagents and their applications in organic synthesis. So in this week's video lectures also, there were two video lectures where Pansar has discussed another few organometallic reagents. So we are going to solve a few more examples, or we will see some more different reaction mechanisms, how those organometallic reagents give reactions. Okay, and most of these reactions follow similar reaction mechanisms as discussed in the previous tutorial. Okay, just like hydroalkoxylation, hydroarylation, those topics we have already covered in the last tutorial. So in today's tutorial also we are going to see some similar reaction mechanisms. Okay, so starting with this fairly easier question, we see that this tricyclic substrate is present and we are treating it with silver acetate in presence of iodine, and the reaction mechanism, if you notice is a protic reaction environment. Okay, so proton source is present and the environment is slightly acidic as well. That means whenever there is a possibility of ring opening using acids, in that case we are going to follow the similar reaction pathway. Okay, so you see that at first this iodination step is involved, and ultimately we are going to get a syn dihydroxylation. So for syn dihydroxylation we have already discussed a few more reagents also. For example, osmium tetroxide we have also discussed. But in case of this silver acetate and iodine condition, this reaction is called Woodward cis dihydroxylation. Okay, so we will go through the mechanism step by step so that you can visualize how this cis diastereomer is particularly forming. Okay, why not trans? So this is the reaction mechanism which is followed in Woodward cis dihydroxylation. We have the olefin first, and in presence of iodine, iodination of the olefin happens and we get iodinium cation. Okay, then we introduce silver acetate in the reaction mechanism. So the acetate anion which is present is going to undergo nucleophilic attack at this carbon, resulting in the opening of the iodinium ion. So this is how the iodinium ion will get opened up, and this carbon iodine bond you see is now absent. Okay, and the counter cation which is silver is coordinating to the iodide. Okay, and after this step, now what happens, the carbonyl group of the acetate which just now underwent the nucleophilic attack is going to form a five membered intermediate carbocation. Okay, so this is how the carbonyl group is going to undergo attack at the carbon atom which is containing the iodine carbon iodine bond. Okay, so because of this attack, if you see, this carbon iodine bond is now going to break. Okay, and silver iodide byproduct is formed in the reaction. See, the coordination of Ag plus and iodide was already present in this step. So, as soon as the carbonyl group attacks at the carbon, this bond breaks and a new bond is formed between the silver cation and iodide. Okay, so this is how we get this silver iodide byproduct and the five membered carbocation intermediate. So remember, the reaction environment at the beginning we talked is aqueous and slightly acidic. Okay, because acetic acid is present and water is also present in the reaction medium. So till now iodine has done the iodination and then the silver acetate has underwent nucleophilic attack. Now the water molecule present in the system is going to form an oxonium ion at this oxygen atom. Okay, so protonation of this oxygen atom will take place and it will lead to the ring opening of this five member ring. Okay, so in this particular step you can see that the ring has already opened, and this is how we have two possibilities of the ring opening of these two. Okay, and because of this ring opening after the protonation, we particularly get the cis diol. Okay, because if you see, both these bonds will lie in the same phase since it is originating from a five membered carbocation intermediate. Okay, so after the ring opens, after opening also, both these bonds are lying in the same phase. So after the ring opening, this acetate will now undergo hydrolysis, because in the reaction if you see, acetic acid is also present. So this acetate ester functionality will undergo acid hydrolysis to give us diol. Okay, so doesn't matter how you are opening the five membered ring, because either you get the hydroxyl at this carbon or this carbon. In both these cases we are going to get the same exact same product, which is going to be the cis diol. So this is the mechanism of Woodward cis dihydroxylation. So if while solving organic synthesis questions, or if you are carrying out hydroxylation reaction in laboratory, now you have another reagent to get a cis diol. Okay, which is this iodine and silver acetate in presence of protic environment. Now let us move to the next question, where if you look at the reaction conditions, those are quite similar to the previous question. Okay, very minor differences are present in this question. So what are those minor differences? If you see, one is the solvent. Okay, the solvent which is used in this second question is different, which is benzene in this case, which is an aprotic solvent. And the second difference in the reaction condition is going to be this potassium hydroxide solution. That means this time the reaction environment is not acidic, rather it is basic. Okay, so these two are the differences in this second question, because in the previous question as a solvent we were using water, and in this later stage we used acetic acid, but here we are going to take the solvent to be benzene, and also we are going to introduce potassium hydroxide in the reaction medium. So let us see how, starting from the similar substrate and using the same reagents, we are going to get transdiol this time. Okay, so let us go to the mechanism step by step. So this reaction is known as Prevost modification of Woodward dihydroxylation. Okay, so always remember the Woodward dihydroxylation is going to give you cis diol, and its Prevost modification is going to give you trans diol. So the first two steps are exact similar in this case also. Okay, the olefin is going to get iodinated and you get this iodinium ion intermediate, and then it is going to be introduced to silver acetate, where the acetate anion is going to undergo nucleophilic addition to the iodinium ion. Okay, so this is the, till this stage, this is the same intermediate. Even the next intermediate is also same, which is this one, this 5 membered intermediate, which we can obtain after the elimination of silver iodide. Okay, so now this intermediate will give us cis or trans is going to be decided from this particular stage. Okay, so in the previous reaction, if you remember, we had acid which was going to form an oxonium of this 5 membered intermediate, but this time we have basic condition. Okay, so oxonium ion cannot form in this particular reaction. In this case, what happens, we have only acetate anion present in the reaction medium, which is going to open up the 5 membered intermediate, and this ring opening reaction is going to follow SN2 mechanism. And as we know that SN2 mechanism leads to the inversion of stereochemistry, that means it is going to attack at this carbon from the opposite face of this substituent. Okay, so this is how these two acetate substituents are going to occupy two different faces. Okay, and at the end, in presence of potassium hydroxide solution, both these two phenyl acetate are going to undergo ester hydrolysis in presence of base. Okay, so basic hydrolysis will happen to give, to convert this ester into alcohol functionality, and thus we get trans diol by following this Prevost dihydroxylation mechanism. So there are minute differences in the reaction conditions which lead to different stereochemistry of the products. You can remember as acidic condition is giving us cis and basic condition is giving us trans diol. Okay, I hope these two reactions are now clear to you, and if you want to revise these two reactions, you can follow the first video lecture of week 11. Okay, moving to the next question. This question is from the part organo silver reagents. Okay, so there were a lot of reactions discussed in the first video lecture, where sir has shown silver mediated nucleophilic attack on alkyne, alkenes and allenes. Okay, so we are also going to discuss a few reactions of the same topics. So this, we have a diwyne compound and in the reaction condition we have an alcohol. Okay, so if you notice here, R2 can be methanol, isopropanol, tertiary butanol. Various primary alcohols are used in the reaction. Okay, and if you notice at the catalyst, it is hexafluorosilver antimonate. Okay, so only 5 mole percent of the catalyst is required for the reaction, and the and yield of the reaction is 73 to 99%. So if you look at the product, and if we see what changes are taking place in the reaction, this carbonyl group which is present here is now linked to this carbon atom. Okay, because R is here, R is here, and this oxygen is linked to the carbon containing the R group. Okay, and not only here, at this alkyne part also changes are taking place, because if you see, R1 is here and R1 is here, and the incoming alcohol is now linked to the carbon atom which is containing R1. Okay, so the while solving the mechanism of these questions, you have to figure out what are the changes that are taking place on the substrate to form this cyclic product. Okay, so now we know what are the changes that are taking place. So this alkyne is now converting into an alene, and the carbonyl is now linked to the upper alkyne. Okay, so let us go through the mechanism how this reaction is taking place. So at first what happens, we have silver antimonate catalyst. Okay, and silver and gold catalyst are known to activate alkynes. Okay, alkyne can very nicely get coordinate to silver and gold catalysts. So at first you can show the coordination of the alkyne to the silver catalyst. And due to this coordination, we have a possibility of turning this alkyne into an electron deficient moiety. Okay, so this alkyne now can form in situ a electron deficient carbocation. Okay, so as a result you can expect the formation of carbocation at this position. That means if you show the intermediate vinyl carbocation, here we are going to have R, here we are going to have positive charge, and here you can show the direct bond formation with silver, and this side phenyl ring will be present. Okay, now if you see, this carbonyl group is now in a very near periphery of this vinyl carbocation. So this will undergo attack at the vinyl carbocation in this way. And after the attack, you can see that the oxygen atom is now taking up a positive charge, because the electron donation is happening from oxygen to the vinyl cation. Okay. After this, to neutralize this oxonium that is forming newly is going we will have the nucleophilic attack from the alcohol which is present in the reaction medium. So this R2OH is now going to attack at the second alkyne, and the electron push you can show first here, and then the oxygen atom will be neutralized. So ultimately you get the R2O linking to this carbon, this particular carbon of the alkyne, and we get this alene product as the final product. Okay, so this is how this cyclization reaction is catalyzed by the silver catalyst present in the reaction. And you can notice that very small amount of the catalyst is required for the reaction. That means very small amount of silver catalyst is enough to lead to the formation of the vinyl carbocation. Okay, that means this alkyne is highly reactive towards silver catalyst. So in case of gold also, you can expect the same type of reactivity for these cyclization reactions. So again, this is another question which is exact same mechanism. Okay, what will happen after seeing the last mechanism? This reaction now must be very easy for you. At first, this alkyne will be activated by silver catalyst, and then you get a vinyl carbocation at this carbon. Then this vinyl carbocation will be attacked here. So if I write the intermediate that is going to form, this will look like this. The phenyl ring is here, and this oxygen atom is linked to this carbon, and the electron push, if you show in this way, you can show the bond formation between carbon and silver. And here you have another aryl substituent. Now, when there are protic sources present in the reaction medium, or during workup stage of the reaction, this carbon silver bond will be broken, and we are going to get this olefin as the final product. Okay, this carbon silver bond will break, and this carbon ion will be protonated by taking a proton from methanol. Okay, so this was an easy reaction. Moving to the next question, where this time nitrogen is going to act as the nucleophile. Okay, so in last questions we have seen the nucleophilic attack by oxygen, and in this question the nucleophilic attack will happen via nitrogen. Okay, and these reactions are called hydroamination. And if you look at the reaction conditions, we have LHMDS in presence of silver triflet reagent. Okay, and silver triflet catalyst is required in only 15 mole percent. 15 mole percent means if we are taking the substrate 1 equivalent, then silver triflet amount will be 0. 0.15 equivalent. Okay, so very less amount of the catalyst is enough. Let us see how this reaction is happening, and despite using such a low amount of the catalyst, we are getting excellent yield of the pyrrolidin product. Okay, so let us see how this reaction is going to take place. So this is the reaction mechanism. At first, what will happen? Silver, like we have seen in the previous questions, is going to activate the alkyne. Okay, and by this, by as a result of this activation, we get a vinyl carbocation in a very similar way that we saw in the previous question. In this side, we get a vinyl carbocation because we have the possibility of forming a stable cycle, which is the 5 membered heterocycle. So after the formation of this vinyl carbocation here, the nitrogen atom is going to attack at this carbon, and we can also show the bond formation between carbon silver. So this is how we are going to get this pyrrolidin ring. Okay, and this carbon silver bond is going to break at the workup stage, where this bond, after the breakage of carbon silver bond, is going to get protonated. Okay, so after this, again another question which is similar, where nitrogen is acting as nucleophile and alkyne attack is taking place for heterocycle synthesis. So if we look at the mechanism, this carbon nitrogen double bond of this heterocycle is attacking the activated alkyne, okay, to form this nitrogen carbon bond in this intermediate. And we see that by the electron movement, this carbon silver bond is forming. After this, aromatization happens, which is taking place by the result of deprotonation. That means neutralization is taking place to give the final product. Okay, the reaction mechanisms are all same. Okay, at first the alkyne activation happens, and then the heteroatom is going to undergo nucleophilic attack on the activated alkyne. Now let us look at nucleophilic attack of oxygen on allenes. Okay, how they are going to take place. Again, we are using silver catalyst here, which is silver nitrate or silver fluoroborate. Okay, and the solvent present is acetone or acetonitrile, and the yield is very good, 72 to 99% of yield. So from an acyclic allene molecule, we are going to get this furan moiety, okay, which is highly substituted also. Let us see how it is taking place. So at first, silver is going to activate this carbon carbon double bond of allene, okay, and as a result, we are going to get a 3 membered cation intermediate of this type. Okay, so after this activation of the double bond, the carbonyl group which is present in the alene substrate is going to undergo attack at this carbon atom, resulting in the bond formation between this internal carbon atom and the silver ion from the catalyst. And after this, deprotonation will take place to form this aromatized stable product. And during the workup, this carbon silver bond is broken and is replaced by a proton to give this furan as the final product. So in alene, as you see that this outer double bond is getting activated, which is leading to the formation of a five membered stable ring as a result of a nucleophilic attack of oxygen on the alene fragment. Okay, so let us move to similar questions. Now we have an alkyl halide which is R2X, and this alenic acid, is present in presence of palladium catalyst and silver carbonate catalyst. Okay, and reaction medium, if you see, is slightly basic in presence of K2CO3 base. Okay, and this furanone is going to be the final product. So this is the mechanism for this particular reaction. Let us see how these alkyl halide and palladium is playing a role in this particular reaction. So at first the reaction mechanism will be same like we saw in the previous question. This bond will be activated and this oxygen atom from the acid is going to attack at this carbon, because in this way we are going to get a stable ring formation. Okay, I have shown the wrong oxygen. Okay, so this will attack at this position, and in the similar way which we saw in the previous question, here carbon silver bond formation will take place after breaking the three membered intermediate. So 107 intermediate we have arrived at. Now what happens? We have this palladium catalyst and R2X in the reaction medium. Okay, so these two will undergo in situ reaction to generate R2PDX. Okay, and formation of these kind of palladium complexes we have already come across in case of coupling reactions like Sonogashira, Heck, Suzuki, via oxidative addition of alkyl halide on the palladium 0 metal. Okay, so in the similar way here also R2PDX complex will be generated, and this R2PD part is going to replace this silver atom. Okay, and as a result you can see that X from here is going to be knocked out, and silver from this intermediate product is going to be knocked out, and the byproduct formed in the reaction will be AgX. Okay, and this AgX will be the byproduct of this reaction. So this PdR2 is going to replace the silver atom of the intermediate product. After this replacement, now in Worka, this particular metal complex undergoes reductive elimination to give the coupling of R2 and the furanone, and we get the 109 compound as the final product. Okay, so this furanone molecule we are going to get if the reaction condition is containing palladium catalyst in basic medium. Okay, let us move to the next question. Again, this reaction is showing the synthesis of this conine natural product. Okay, this is a biologically active natural product, and if you look at the substrate, this reaction is going to involve nucleophilic attack on allene from nitrogen. Okay, in the previous two questions we saw attack on allene by oxygen, and this case the attack is going to be by nitrogen, but the mechanism involved will be very similar. So what will happen, again this particular bond will be activated by silver. Okay, and we are going to get a three membered intermediate of this kind. This is basically the transition state of this reaction. Okay, here you have to show positive charge, and here we are going to have hydrogen methyl, and here the other double bond. So after this activation, this is the positively charged intermediate we are going to get, and after this the nitrogen atom of the substrate will undergo hydroamination reaction to open this silver containing three membered ring to give us a stable six membered piperidine ring of this type. Okay, so this is how we can show the piperidine ring synthesis starting from this aminoallene, and by reducing this carbon carbon double bond and deprotecting this benzyl group from nitrogen, we get this biologically active natural product conine. Okay, so again the mechanism was very similar. The double bond is first activated, and then the nitrogen atom undergoes hydroamination reaction to give us more stable six membered ring product. Now we have nucleophilic attack on alkenes, okay, which comes from the last part of the organosilver reagents, which was covered in the first lecture of this week. Okay, so let's just look at this mechanism. So if you see the reaction condition, it is carried out in presence of silver nitrate catalyst in ethanol solvent at room temperature, and the substrate has this carbon cyanide bond and this alkene. Okay, if we notice the net result in the product formation, what is happening is this hydroxy group is getting converted into ketone, This six membered ring is getting expanded into a seven membered ring, and a new five membered ring is forming, which is obviously by the attack of this nitrogen to this alkene. Okay, so we will see how this nitrogen is going to form this five membered ring, and the six membered ring is going to expand. Okay, let us see the mechanism. So the reaction mechanism starts with elimination of silver cyanide. Okay, the silver cation is going to take up this cyanide, leading to silver cyanide elimination, and we get a positive charge centered on the nitrogen atom of this substrate. Okay, so we get this diene intermediate product as an intermediate of this reaction, and this diene now undergoes 3,3 as a cope sigmatropic reaction. Okay, you see this bond, this carbon carbon bond is going to undergo 1 2 3, 1 2 3, 3 in both sides. Here you see 3 in both sides from the carbon atom. So 3 3 sigmatropic rearrangement we can expect. Okay, and as a result this sigma bond is now transferring to the terminals of the diene. Okay, so this intermediate we are going to get now. After this step, what happens, this oxygen lone pair will push up. Okay, I'll show separately so that it is better to understand. We have this hydroxy group and this double bond here. Then we have the positively charged nitrogen atom. So this oxygen atom is going to push its electron pairs towards the double bond, and this double bond will undergo attack at this carbon atom, which is basically following the Mannich cyclization, and the nitrogen atom is going to be neutralized. Okay, so if we count number of carbons in the ring, it will be 1 2 3 4 7. So this is how a new 7 membered ring is formed, where the initial hydroxy group is now replaced by this ketone. Okay, so this is how the reaction is going to involve silver cyanide elimination, then a 3,3 aja-cope sigmatropic rearrangement, and at the end the reaction will follow Mannich cyclization. Moving to another question, This is another easy question where you see that this bromine containing pyran cycle is present, and again silver catalyst in aqueous acetone is taken. Okay, and if we see the product, the ring of the cycle has decreased by one carbon. Okay, initially it is a pyran saturated cycle, and at the end we are getting a cyclic ether which is 5 membered ring. Okay, so at first what happens, the silver cation is going to react with the bromine. Okay, silver metal has very high affinity for halogens. Okay, always remember. So this is how AgBr elimination is highly feasible from the substrate, and as a result of AgBr elimination we are going to get a positive charge at the carbon atom which is containing the bromine atom, and that positively charged carbon atom can be attacked from this oxygen atom present. Okay, and if the oxygen is giving up its lone pair to the positively charged carbon atom, now this oxonium ion will form. After this, ring will ring size will decrease by the breakage of this carbon oxygen bond, which happens to neutralize the oxonium ion that is forming in the reaction. Okay, so this 5 membered ring, 5 membered cyclic ether is going to be the final product. Now moving to this next question, where again silver is catalyzing this reaction between aldehyde and this silyl containing bicyclic moiety. Okay, so this reaction mechanism might look like a little difficult to you, but if you try to understand it step by step, then we will know that how the atoms are playing their parts in the reaction mechanism. Okay, so the reaction mechanism starts with attack of fluoride from Kf at this silicon. Okay, always remember fluorides have very high affinity towards silicon, due to which fluorinated reagents like TBAF, TBAF is nothing but tetrabutyl ammonium fluoride, or HF pyridine solution is used to deprotect silyl protection of oxygen atoms. Okay, you have already known TMS, TBS, TIPS are the silylated protecting groups of oxygens. So due to the high affinity of fluoride anions towards silicon, these reagents are used to desilylate oxygen atoms. Okay, so the reaction here also starts with the attack of fluoride at silicon, leading to the breakage of this 7 membered ring. Okay, so you are going to get an intermediate of this type. Okay, this SiMe2F part remains in a ring, and This part, if you see, is now linked to the benzaldehyde ring. Okay, and this benzaldehyde ring also, if you see, is getting activated with the help of the silver catalyst. Okay, both the carbonyl groups, one from the aldehyde and one from the ester, is getting activated by the silver. So after the formation of this 326 intermediate, rearrangement reaction takes place, and you can see that this oxygen, which is containing the oxygen silicon bond, attack attacks at this particular carbon atom to undergo ring closing reaction, and this particular part, if you see, will lead to the breakage of this carbon oxygen bond first, and this silver oxygen linkage also breaks, and this side also this silver oxygen linkage breaks to give us an oxyanion, which can take up proton to get this alcoholic functionality. Okay, so this is how, in presence of silver triplet catalyst and potassium fluoride salt, we get this particular product. Okay, now coming to organorhodium chemistry. Okay, we are going to see how two alkyne fragments can undergo reaction in presence of rhodium catalyst. Okay, so this is the substrate with which we are going to start the reaction, and this is the rhodium catalyst where this biphenyl ligand is linked. Okay, and rhodium metal used in this reaction is in +1 oxidation state. So at first we have this diwyne substrate which gets activated by the rhodium metal, and this activation will lead to this ring closing reaction to give us this particular intermediate product. Now another external alkyne we are going to add, because if you see the ultimate product, actually we are forming a phenyl ring starting with a diwyne. Okay, from this substrate, by treating it with an external alkyne of this type, we are going to get an aryl ring. Okay, from three alkyne fragments we are going to generate this phenyl ring. So we have arrived at this stage where we have introduced the external alkyne. Now this alkyne is also getting coordinated to the rhodium metal, and we expect the insertion of this newly coming carbon carbon triple bond in between this rhodium carbon bond. Okay, so now from this five membered ring and this external alkyne, we are getting metalla cycle which is containing fused 5 and 4 membered rings. Okay. Now this methyl cycle will undergo ring opening because this cyclobutene fragment which is newly forming is highly sterically unstable. Okay. So this 4 membered methyl cycle and 5 membered methyl cycle will immediately undergo ring opening to give us this 7 membered methyl cycle now. Now at this stage, this methyl cycle intermediate will undergo reductive elimination to give us couple of this carbon atom and this carbon atom. That means you can imagine a bond that is forming in between these two carbon atoms, and thus we get this phenyl ring as a result of this reductive elimination. Okay, and in the workup stage, the coordination with the rhodium catalyst will break and we are going to get our desired aryl ring formation from the three alkyne fragments. Okay, so the coordination, oxidative addition, and reductive elimination, all these steps you have already come across in various coupling reactions. Okay, so this is how using rhodium catalyst we can use highly functioning aryl rings. Okay. Okay, so this is another question from the rhodium organorhodium chemistry. So you can take this catalyst 9 to be the same catalyst as the previous question. This rhodium catalyst in +1 oxidation state in 1 mole percent can give us this oxygen silicon bond formation starting from cyclobutanone and dimethyl phenylsilane. Okay, so let us see how this reaction is taking place. Starting from a ketone, we are getting this oxygen silylated alcohol. Okay, so this is the simple reaction mechanism which this reaction is going to follow. Okay, at first we have this rhodium catalyst which will undergo oxidative addition with the trialkyl silane. In this case we have this dimethyl phenylsilane. So the dimethyl phenylsilane will undergo oxidative addition to the rhodium metal. After that, the carbonyl coordination to rhodium will take place, and this type of interaction between the carbonyl oxygen and the rhodium metal will be seen. Okay. After the coordination, now the carbonyl group will undergo insertion between this rhodium and silicon bond. Okay. So this is how the carbonyl oxygen insertion takes place. And at the end, what happens? Reductive elimination will lead to the coupling between this hydrogen and this particular carbon. Okay, and this rhodium catalyst is regenerated. So this is how we get silyl protected alcohol as the final product. Moving to this organonickel reagent, where you see this aryl halide is present and a second halide which is alkyl halide is also present, and These two halides now are undergoing coupling reaction in presence of nickel catalyst to give us this final product. Okay, if you remember, in case of various coupling reagents, for example, if we talk about Sonogashira coupling, that happens between an alkyne or a vinyl with aryl halide. Okay, so various coupling reactions, if we remember, occurs between vinyl or aryl halides and aryl iodides. Okay, but in this case we have both iodides. Okay, aryl iodide, aryl halide, and alkyl halide. So two different halides are undergoing coupling reaction to give us a third hydrocarbon in presence of nickel catalyst. Let us see how this reaction mechanism is going to take place. So the mechanism is divided into two parts. Okay, first part is known as polar oxidative addition reduction, and the second part is known as radical chain. So the first part is going to involve the ionization mechanism, where we are going to get oxidation reduction, and in the second part radical formation happens. Okay, so this is how the mechanism has been proposed. So if we look at the mechanism, it starts from here. Okay, this nickel catalyst we have, in which the nickel metal is present is in zero oxidation state, and the aryl halide which is used in the reaction will undergo oxidative addition to the nickel catalyst. Okay, then this oxidative addition, after forming this nickel plus 2 metal complex, the radical CH2R which is generating by the radical chain of the alkyl halide. Okay, remember we had aryl and alkyl halide. So this alkyl halide undergoes radical formation by homolytic cleavage of this carbon iodine bond, and we get this CH2R radical, which gets added to the nickel plus 2 metal complex, leading to the oxidation of nickel plus 2 into nickel plus 3. Okay, now this nickel 3 metal complex undergoes reductive elimination to give us coupling between this aryl ring and this alkyl chain. Okay, so both these two will combine after the reductive elimination to give us the third hydrocarbon as the final product. Okay, so via these two different mechanism cycles, we involve both oxidation reduction and radical chain for the oxidation of Ni2 to Ni3. Okay, moving to the next question from the part organonickel reagents, where you can see this imine is going to be added to the alkyne. Okay, and the reaction is catalyzed by nickel catalyst. Let us look at the reaction mechanism. So just like we have discussed the hydroamination reactions, the similar reaction pathway will be followed here again. So the mechanism starts from here. The alkyne is first getting coordinated to the nickel metal, and the imine is attacking at the activated alkyne. Okay, as a result, since this imine is donating electron pairs, this imine will get positive charge, and this carbon nickel bond formation can be showed. Okay, so this intermediate B will form by anti-amino metallation. So after the formation of this metal complex, proton transfer will take place from this positively charged nitrogen atom to this carbon atom, leading to the breakage of this carbon nickel bond. Okay, so the nickel metal is regenerated for another cycle, and we successfully get the hydroamination of this imine on alkyne, which is nickel catalyzed. Then another reaction which is showing coupling reaction between alkyne and this alkyne pyridinium salt in presence of nickel catalyst. Okay, and L4 is nothing but the ligand which is going to be used. So this is the reaction mechanism. Do not get scared by looking at the structure, because this huge thing which you can see is nothing but the ligand only. Okay, the reaction is happening on the alkyne part. Okay, just focus on the alkyne part. So at first what happens, the alkyne will react with the nickel catalyst in presence of the L4 ligand, which is this huge ligand, and in presence of potassium phosphate we are going to get the oxidative addition of the alkyne to get the intermediate metal complex A. Then another molecule of the alkyne is coordinating to the nickel metal to give us the intermediate metal complex B. And now finally the alkyl pyridinium salt is going to be introduced in the reaction, and the oxidative addition of this alkyl pyridinium salt will take place to give us this alkyl carbon nickel bond formation. Okay, and the nickel metal will get oxidized from -1 to +1. Okay, from +1 to +2. Okay, and after this reductive elimination will take place, which will give the coupling between this alkyne fragment and this alkyl fragment. Okay, so these two will leave to give us the final product which is shown here, and this intermediate A is now again regenerated and it is ready for another cycle of the catalysis. Okay, so this is how this nickel catalyzed coupling reaction will take place between alkyne and alkyl pyridinium salt. Moving to the next topic, which is organoplatinum reagent. Okay, so in the second video lecture of this week, Adams catalyst topic has been covered. It is nothing but a hydrogenation method of olefins, and you must know that this catalyst which uses platinum oxide is highly expensive. Okay, and usually it is preferred that platinum metal is freshly oxidized into platinum oxide to be used as Adams catalyst. Okay, otherwise, if you prepare platinum oxide and try to store it, it gets spoiled. Okay, it cannot be stored for a longer period. Okay, this is how it is advised to prepare Adams catalyst always freshly from platinum metal. Okay, so as you see that hydrogenation of this olefin using Adams catalyst is leading to the formation of major portion of the cis hydrogenation product and only 18% of the trans hydrogenation product. That means in 82% of the product, both the hydrides from the metal surface are coming from the same phase. Okay, both the hydrogens are adding from the same phase. So if you revise the catalytic hydrogenation mechanism, it works upon the adsorption mechanism. Okay, how the hydrogen molecule and the substrate olefin gets absorbed on the metal surface and the hydrogen atoms are transferred from the metal surface to the olefinic substrate. Okay, so you can imagine this is the metal catalyst surface where our hydrogen molecules and the olefin are lying. Okay, and when the reaction happens, the olefin takes up hydrogens from the metal surface, which leads to the breakage of the coordination, which is nothing but physical adsorption between the metal surface and the hydrogen atom. Okay, and thus one by one, two hydrogens are taken up by the olefin from the metal surface, leading to the hydrogenation of the olefin. Okay, since both the hydrogens are getting added up from the same phase, this is how we always get a cis hydrogenated product as a major product in catalytic hydrogenation reaction. Okay, so this is a mechanism which is also followed in the Adams catalysis. Then we have this particular industrial process which is known as carbonylation of methanol for the formation of acetic acid. Okay, so this process is also discussed in the second lecture of this week, and this particular reaction is mediated by iridium metal complex. Okay, let us see how industrially acetic acid is synthesized using iridium metal complex starting from methanol and carbon monoxide. Okay, so this is the reaction mechanism. So the mechanism starts from, let me show you step by step. Mechanism starts from here. Okay, methanol is taken and it is first reacted with hydroiodic acid HI. Okay, and reaction between methanol and HI will give us methyl iodide in the reaction system. Now we have this iridium plus 1 metal complex. Okay, this iridium metal complex will undergo oxidative addition with the methyl iodide which we are getting from methanol and HI. Okay, and this is how we are going to get this new iridium metal complex where the oxidation state of iridium plus 1 increases by 2. That means in the metal complex 2, the iridium metal is now having plus 3 oxidation state. After this, it will undergo iodide elimination and another molecule of carbon monoxide, which is the carbonyl, coordination to the iridium metal. Okay, so this is how we get the intermediate metal complex 3. Okay, now what happens, this intermediate product 3 will undergo carbonyl insertion between this iridium metal and the methyl fragment. Okay, this carbon monoxide undergoes carbonyl insertion, and this carbonyl insertion as a result will react with the iodide which was getting eliminated at the beginning, and the reaction between this metal complex and this iodide will lead to the formation of CH3COI product. Okay, this acid iodide or acid halide is formed due to the reaction between this metal complex 4 and iodide. Okay, and since in the reaction medium we have water, the acid halide undergoes carbon halide bond cleavage and hydrolysis to give the desired product, which is acetic acid. Okay, so this reaction is widely used for the synthesis of acetic acid starting from methanol and carbon monoxide. Okay, so this is how we have covered all the questions from today's tutorial on the topics covered in the week 11. Okay, so a lot of questions we have discussed. Let us go one by one through all the questions and have a quick recap. Okay, we started with Woodward cis hydro dihydroxylation, where we saw that if we are taking silver acetate and iodine in aqueous medium in presence of acidic environment, we can expect cis dihydroxylation of this olefin. Okay, so this reaction we discussed. We also went through the reaction mechanism, where this particular step played a very important role because it is undergoing protonation to give us oxonium. But we saw if we are carrying out the same reaction in basic medium, we can expect the formation of transdiol, okay, which is also known as Prevost modification of Woodward dihydroxylation. Then we saw the nucleophilic attack of oxygen on alkyne to form these allynic ethers. Okay, and we also discussed the mechanisms. Similar reaction was observed where this phenol attacked at the activated alkyne, which was activated by silver, and the ring 5-membered ring formation was found to take place. Then we saw the nucleophilic attack of nitrogen on alkyne in presence of base and silver triplet. Similar mechanism was followed. The alkyne was activated by silver catalyst and nitrogen atom was undergoing hydroamination reaction. Then we have a again similar reaction. The nucleophilic attack was taking place from this ring nitrogen, which is carbon nitrogen double bond, to the activated alkyne to give us a tricyclic heterocycle. Then we came to the nucleophilic attack of oxygen on allenes catalyzed by silver, and we saw the formation synthesis of furan starting from acyclic allenes, and the reaction involved the activation of the outer double bond and attack of this carbonyl to the three-membered cation intermediate, to give a five membered carbocation. Okay. Then another example we came across for the nucleophilic attack of oxygen on allene, where we saw that palladium catalyst was also used, which involved the replacement of the silver metal by the palladium metal, and at the end reductive elimination. Then we also studied hydroamination of this nitrogen atom to allenes, okay, for the synthesis of biologically active natural product conine. And then we saw the reaction where we saw this six member ring was converted into a product which is containing fused 7 5 rings and catalyzed by silver nitrate. Okay, and we discussed the reaction mechanism, which involves 3 3 sigmatropic rearrangement and also manic cyclization at the end. Then we saw this easy reaction mechanism where a six membered cyclic ether was seen to shrink into a five membered cyclic ether. Then we discussed this reaction between substituted benzaldehyde and this O oxygen silicon bond containing bicyclic fragments, where we saw that the reaction started because of the high affinity of fluoride ions towards silicon. Okay, and then we saw the synthesis of aryl rings starting from three different alkyne fragments. Okay, and we also discussed the protection of this oxygen atom of cyclohexanone using dimethyl silane and rhodium catalyst. Then we came to the coupling of aryl halide and alkyl halide using nickel catalyst, where we saw the involvement of radical chain also. Okay, then we studied the nucleophilic attack of imine on alkyne catalyzed by nickel. And then another coupling reaction we studied between alkyne and alkyl pyridinium salt in presence of nickel catalyst, where we saw that at the end the alkyl fragment from the alkyl pyridinium is linking to the alkyne. Then we talked about Adams catalyst and its mechanism, how it always prefers to form cis hydrogenation product. And at the end, we discussed the industrial synthesis of acetic acid via carbonylation of methanol. Okay, so I hope all the concepts from today's lecture were clear to you. We will meet for the last tutorial of this course on next Friday, and after that we will have a summary tutorial most probably on the next week. Okay, so
Okay, thank you, madam.
thank you so much for joining.
Thank you.